All right, so let's go ahead and get some practice on applying our knowledge from our last one to an actual example. So in this case, we're going to go through and we're going to look at a generic reaction, which we have written out here in example 2. And we're going to go through and describe what is going to be our acid, what's going to be our base, as well as thinking about what is the mechanism or what's the process we can show to get between our two. Now, before there, I do want to go ahead and mention one thing, which is going to resolve around the idea of spectators or a spectator ion. A spectator ion is going to be a cation, which is going to be our positive charge species, that is not going to participate in our reaction. And our most common spectators are going to be our group 1 and group 2 elements. And if we kind of think of a few specific examples, lithium with a plus charge, sodium with a plus charge, potassium with a plus charge. You can also have your 2 pluses of like your beryllium or your magnesium, or the other one is calcium. Each of these are group 1 and group 2 elements are going to be forming a ionic bond. So that's just going to be that kind of charge attraction between a positive cation and a negative anion. So a lot of times when we think about bases, we think about, so for example, sodium hydroxide, NaOH. Here we have a specific example of lithium hydroxide, or LiOH. Anytime we see our spectator ions, which are group 1s or 2s, so lithium, sodium, potassium, beryllium, magnesium, calcium, we're going to redraw our structure to give a better representation of what it actually looks like. So when I look down here at my lithium hydroxide, my lithium right here is going to be a spectator, and that's really just going to leave me with my OH minus. And overall, we'd have 3 sets of lone pairs on that oxygen. With that, we'll often just simply draw 1, which is going to be the one that actually reacts. So anytime you see something like NaOH, it's just think of OH minus. LiOH, just think of OH minus. Same thing here in our kind of product. Here we see that kind of ionic interaction between that oxygen and that lithium. So here we can think of this the same as just our deprotonated carboxylic acid. So let's go ahead and first start by just identifying what is my acid and what is my base, and therefore my conjugates. And the easiest way to do this is just simply looking at which compounds pair together. So here I see that my first compound on both my reactants and my products looks super similar. They both have that carbonyl, that carbon double bond with an oxygen, and that's going to make my other 2 components paired together. So those are going to be the conjugate pairs. So this one here is going to pair with like this one here. So of those 2, if I look, for example, at my very first structure, I have a carbon, a double bond to an oxygen, and then a single bond to an oxygen, which is bound to a hydrogen. If I look at the product, I have everything the exact same, except my oxygen now carries a negative charge and is no longer bonded to an H. So in this case, this hydrogen that is connected to my OH does not appear in my products in the same spot, meaning that this compound has to be my acid because I'm losing or donating that proton. If I am an acid in the Ford reaction, my product must be a conjugate base. You're going to switch and have the opposite role in order to have this be equilibrium. This equilibrium, where there's 2 arrows in the opposite direction, means that the reaction is going to go back to make the starting material. So if I'm an acid, meaning I lose a proton, in the reverse reaction, I have to gain a proton. Therefore, I must be a base in the reverse. So that's why we have an acid and a conjugate base. Once you identify the acid, then you're good because the other one has to be a base. So here, my hydroxide ion is going to be my base. When I draw it out as this OH minus rather than this LiOH, if I ever see that negative charge, that's going to be a big hint that I'm going to be a base. Same thing if you look at the product over here, that conjugate base, you see that negative charge, and that's going to tell you some base stuff. So that's going to be my base. And then the product of that, which is going to be my water, which is just going to be my OH with an extra H on it, must be my conjugate acid. So I have my acid, my base, my conjugate base, and my conjugate acid all drawn out here. Now that we've identified these, let's go ahead and actually show the mechanism or the process in which we get from our starting materials to our products. And here I'll go ahead and just redraw all my starting materials. It's always a good idea to redraw them, especially because a lot of times this would actually be drawn as just this OH, and they wouldn't often show this explicit bond right here. I've shown that there just to kind of get you practice of seeing them, but in a lot of problems, that bond is not going to be drawn. So you're going to need to make sure that you physically see that bond in your acid. And then this is going to react with our OH minus. So from a mechanistic standpoint, we're going to always start with our base, and we know our base is going to be this hydroxide ion, and we're going to start at our lone pairs, and then we're going to draw an arrow to whatever it is stealing, whatever bond it's making to. And that bond that it's making is going to be this extra bond that we now see when we now have our water. So this is kind of like this bond right here between this oxygen and this second hydrogen. That is being shown by this first arrow as we go from our lone pair to our proton that we're abstracting. Now, when I think of my products, my conjugate base has a total of 3 sets of lone pairs. So I need to get that third lone pair on it. And I'm going to show that by breaking this bond and putting those electrons on that oxygen, which is getting this extra set of lone pairs on my conjugate. So these are going to be the 2 sets of arrows I'm going to show, a making of a bond and a breaking of a bond that are going to be used in my acid base. And that's going to give us our kind of like full mechanism as well as our kind of labeling of our acids and our bases. Now, sometimes this can be a little bit more involved, and we can also kind of assess a lot of that same knowledge without actually having you go through and draw out this entire process. So let's go ahead and ask kind of a similar question, but in a really, really different way. It's the same concept, a very different way. Let's go ahead and look at example 3. What is the conjugate acid of CH3NH2? Now, this is going to require 2 things. First, we're going to need to kind of draw the product, but we also need to try to figure out, what is actually going to be happening to this product? And when we think about the fact that we have a conjugate acid, our conjugate acid is going to be our base plus our proton. So this is if we start as a base, the product is going to be our conjugate acid. So here, because of the fact I'm asking for a conjugate acid of this species, that means this species must be the base. So we can draw out our structure here. I'll go ahead and draw this out kind of again as a Kekule rather than a Lewis structure. So our CH3 and then NH2, this is going to have to serve as a base because we want to see the conjugate acid. And that conjugate acid is going to be what is formed when this acts as a base. So here, I'm just going to just show a generic H plus as our source. And we are going to grab that proton using the lone pair electrons, which only are going to exist here on our nitrogen. Most of the time, nitrogens and oxygens are going to be some like the most common like kind of species that are going to have lone pairs that we'll see do some acid-base stuff. We can every once in a while do some carbon stuff, but the oxygens and the nitrogens are going to be some of our most common. Now, if I wanted to draw the product there, I would have everything be the exact same. The only difference is now, instead of having a lone pair on that nitrogen, I'm going to have an extra bond to our proton, which we just abstracted. And this nitrogen now has 4 bonds instead of 3, which means it's going to carry a plus charge. And this is going to be our conjugate acid. So this is assessing kind of all that same knowledge, but in a very different format where I just give you an individual structure and then say, what's the conjugate acid? You could also do the same thing where you say, like, what's the conjugate base? And if that's the case, then you would actually lose a proton and get a lone pair on one of your atoms. So I think that's a good place to stop for this video. In the next one, we're actually going to go ahead and get a brand new definition of our acids and bases outside of thinking of this actual movement of protons. And we're actually going to use a definition of acid bases that are just purely going to focus kind of like on our mechanisms, our movement of our electrons, and don't actually include any H's at all.